doing something a bit different today, starting with the SQL course, or SQL, whatever you want to call it. Doing this in preparation for my upcoming new work. So, here we go. It's 10. I should not complain.
He kind of sighed and said, "You know, we're not so different, he and I." And over the years, I've come to understand exactly what my manager meant. As backend developers, we take a bunch of data from one place and shovel it into another place. We're really just kind of moving digital garbage around. That's like the whole job. And the best tool for moving digital garbage is SQL, or SQL, or Squeal.
Squeal.
So say you're a programmer at Google working on YouTube. Your job is to write code that shovels data from creators' devices, so a video, a title, a thumbnail, up into YouTube's cloud servers and stored in some database. Then, when users are bored at their sister's graduation, they log onto YouTube to find a meaningful distraction. Your job is to write code that shovels all that same video data back out of YouTube servers and down onto the user's devices. SQL, or structured query language, is just the language that we as programmers use to communicate with most relational databases. And it's so popular that databases are broadly categorized into SQL databases and no SQL databases, or no SQL databases, which really just means everything else. So what is a database? Well, really, it's just a program, usually separate from your actual backend application server, that's built to store large amounts of data on disk, and importantly, to store it in a way that makes it fast to access, with advanced filtering and sorting options. You can kind of think of it like a programmatically accessed Microsoft Excel. Now, with Excel, you move data around fairly manually by pointing and clicking, typing and dragging and dropping. A relational database works similarly, in that data is organized into tables of rows and columns. But it's all managed in code, not manually with mouse clicks. Your code automates the creates, reads, updates, and deletes within the database. The code that interacts directly with the database is, you guessed it, SQL. SQL is just a query language that we use to get data in and out of relational databases like MySQL, Postgres, or SQLite. It doesn't matter if your backend programming language is Go, Python, or TypeScript. If your database supports SQL, you can use SQL syntax to get data about a user named Bilbo out of your database. Select first name, last name, age from users where email equals bilbo@boot.dev.
Feels more accurate.
SQL isn't web scale. Why don't you use MongoDB? MongoDB is a web scale database. Look, maybe you've heard claims like this before, but let's talk about the real differences between SQL and NoSQL databases and look at some of the more popular technologies in both categories. So on the SQL side, we've got Postgres, big favorite of mine. You've probably also heard of MySQL and SQLite. There's SQL Server, which is Microsoft's product, And I'll also mention CockroachDB, which is a pretty cool distributed SQL database. Now, there are hundreds of SQL-compatible databases out there, but these are probably just some of the ones you've heard of. Now, MongoDB is probably the most well-known example of a NoSQL database. In fact, some people even use the terms synonymously, which I think is a big mistake. You've probably also heard of Redis, maybe Elasticsearch. Firebase is another really popular one. It's more than just a database. It's kind of a backend as a service. And I'll also mention DynamoDB, which is Amazon's big data store. Now, the first thing you need to understand about the difference between a SQL database and a NoSQL database is that SQL databases tend to be much more similar to each other. They're grouped together in this category because they all have something in common. They all use structured query language to be queried. But NoSQL databases, really the only thing that they have in common is that they don't use SQL. So they're all very different, and frankly, they're not even built necessarily to solve the same types of problems. For example, if I asked a candidate in a backend interview, hey, would you use Postgres or MySQL to build this CRUD app? And they said either would work just fine, that would make sense. But if I asked a candidate if we should use Redis or DynamoDB for our caching layer, and they said, it doesn't really matter, then there's no way they're making it to the next round. Now, SQL databases tend to be more general purpose. Now, that's not always true, but at the end of the day, a SQL database is just a database that supports SQL. So you can have a more specialized SQL database, but most of the popular SQL databases are good for general purpose starting points for web applications. One exception might be SQLite, which is built for small use cases where you want to embed the database directly inside your application. And NoSQL databases, on the other hand, they tend to be very specialized. NoSQL databases are usually built for a specific purpose that a general purpose SQL database doesn't handle as well. Again, one exception is probably MongoDB, which is a fairly general purpose database. It just happens to not use SQL. For example, Redis is mainly used for caching in-memory data for super low latency access. It's common for web apps to use Redis together with a SQL database, and they use Redis as sort of this caching layer. Elasticsearch is another example of a very specifically designed NoSQL database. It's designed for dynamic search and aggregations. It powers things like the eBay search bar. It handles fuzzy text matching and ranking of results. Another one is Firebase, a Google-hosted product. It's really built for real-time mobile apps. And the last one I'll mention again is DynamoDB. It's built to store very large amounts of data at scale. The trade-off is that you kind of have to denormalize your data, and you can't write the same flexible queries that you would inside a normal SQL database when you use it. The main point here is that an SQL database is any database that you can interact with using SQL syntax, and a NoSQL database is just any database that doesn't have that. When you're deciding which database to use for your application, you really need to weigh the pros and cons for your very specific use case. For most simple CRUD-based web applications, something like Postgres is gonna work just fine. It's a general purpose database that can handle a good amount of scale. But as your application's data grows, or if you have a very niche specific use case, you can introduce other database technologies to your stack at that point.
What's wrong? Either columns. This is wrong. Okay. That's wrong. Maybe it's just displaying info of the table. Okay. Waste of a fucking armor, but that's fine. Don't drop columns. Don't drop tables. Don't drop tables. Never. Not even if there's a backup. You want to lose your job very quickly? Write drop commands. SQL is
Database migrations are kind of like unit tests. Most people suck at writing them, but they do like to talk about how important they are. Now, you're probably doing migrations wrong, or more likely, you're not even doing them. So let's talk about the right way to do them. Say that we have a users table with ID, username, and password columns. The database is currently being used in production, and now it's time to add a new feature, and that feature requires a birthday column for each user. The right way to do this isn't to just connect to the production DB with PSQL and run a quick add column query. The right way is to create a migration file. That add column query goes inside it. And our system should be configured to run our migrations whenever we deploy new code changes. Now, when we want to create a copy of the database, or we need to spin up a new local development environment, we can just run all of our migrations one after the other, and the schema, tables, columns, indexes, that kind of stuff, will always match. Now, this type of migration, where we're just adding a new column or a new table, tends to be really safe. None of the currently running queries in production are going to care about this birthday column, so when we add it, those queries will still work. They'll just ignore the new column. See, a good migration needs to think about two things. One, the old, currently running version of the code, and two, the new version of the code that will run after the migration is complete. A lot of developers forget about the old version. They write a migration, they test their new code on the new schema, and then they just deploy it. But as the migration deploys, the app breaks for the couple of minutes when the old version is still running, but with the new schema. So for example, say we create a migration that removes a password column and adds a Google ID column. Maybe we're no longer storing user passwords because we only support sign in with Google. Now, if we run this migration, but the currently running version of the app runs a select password from users query, then user logins are going to be broken until the new version of the code that doesn't use that field is deployed. So you might think, well, great, let's just deploy the code first. But that doesn't work either because the new code depends on the new Google ID column that's in the migration. So the answer here is to do a multi-phased rollout. Step 1, we run a migration that adds the new Google ID column, and this is safe. Step 2, we deploy the new code that uses the Google ID column, but not the password column. Step 3, we run a cleanup migration that just removes that unused password column. Okay, so creating and removing columns and tables is pretty straightforward, but what if we want to update an existing column? Well, generally speaking, the safest thing is to just not do that. At least not directly. It's okay to add an index to an existing column for performance reasons, because that won't break any of the currently running queries. But what you don't want to do is rename an existing column that's being actively used in production. Instead, we should do another, more complicated multi-phase rollout. Step 1, run a migration to create the new column. Step 2, copy the data over from the old column into the new column. Step 3, deploy the code that uses the new column, but not the old one. And step 4, this is very important, recopy the data from the old column to the new column to catch anything that was missed between the initial copy and the code deployment. And then step 5, just run a migration to remove the old column. Now, to be fair, this is kind of a lot of work. If your team just doesn't have the resources to do that, a cheat some companies will use when the migration gets really, really hairy is just to schedule some downtime. You can literally just turn off your application and tell your customers, hey, the whole site's going to be down for the next 30 minutes while we do a big update to our database. I want to be clear, this should only be a last resort, and you should only do it if the migration's super hairy and you feel like the time trade-off isn't worth it. Most good engineering organizations tend to avoid downtime at all costs. Okay, so you think you're a responsible developer because you write well-documented migrations for your database schema. But what happens when one of your migrations is bad? Normal database migrations, the ones that you run to get your database into the correct state for your application, those are called up migrations. They take your database from the old, out-of-date state into the new, proper working state. Now, to be fair, a lot of engineering organizations get away just fine without writing down migrations at all. They just move forward, and in the event of something going wrong with an up migration, they just roll out another up migration that fixes it. And this really can work, especially if you're on a small team. But as team size and application complexity grows, you usually want some more safeguards in place. In particular, you probably want the ability to roll back a change when something goes wrong. Now, it's always easy to roll back code changes. Just go back to the last git commit and deploy that version. But databases are a little trickier. Say you deploy code that doesn't need a bio column anymore. So you run an up migration that drops that column. Then 10 minutes later, you realize there's a bug in the code. So you need to go back to the old version of the application that requires that bio column. You can't just revert the code anymore because now it's going to break because the bio column is gone. So that's where down migrations come in. The idea is that each time you write an up migration, you also write a down migration that can be used to undo. So if the up migration removes a bio column, the associated down migration re-adds it. If an up migration creates a notifications table, then its down migration removes it. The down migration should always be the inverse of the up migration. And it's really only used in the case of failure or a rollback. Now, it's very important to remember that while down migrations can fix the schema of a database so the code will work, they usually aren't written in a way that will actually recover the lost data. In other words, we can add that bio column back, but all those user bios aren't going to be there anymore. They're just going to be blank. So the code will still work in the sense that the queries aren't going to throw errors, but the data won't be there. So to solve those problems, you need a backup strategy that you can go pull that old data from, but that's another topic.
Figures stored in 0 bytes. Do this and then call it a day for the lesson. Oh, is that all I'm getting out of this chest? Oh well. Well, that's it for the first SQL lesson, or first SQL video. See you in the next one.